Welcome, dear students. In today's class we discuss structure of simple ionic compounds or ionic crystals. In the previous video we learned about the structure of metallic crystals in which there is only one type of constituent particle. But when it comes to ionic compounds, the difficulty is that there are at least two different types of particles. That means anions and cations are there, which are having different size. So how to describe or how to arrange these different particles, that means particles of different size, in the close packing? Generally, it is that cations, which are generally smaller in size, occupy the voids formed in the close packing of anions. That means anions make up the close packing and cations enter the voids. Then comes a question: to which void the cations enter, whether to a tetrahedral void, octahedral void or cubic void? Naturally, that depends on the size of the cation. You remember the type of voids we discussed in the previous video, and the radius ratio, radius of the void to radius of the sphere, we have noted. For tetrahedral void it is 0.225, for cubic void it is 0.414, and for octahedral void and for cubic void is 0.732. So if cation is small enough to enter the tetrahedral void, that will be occupied. If it is bigger, it will go to octahedral void, etc. So here we discuss, first of all, what is called radius ratio rule. Radius ratio means ratio between radius of cation to that of anion. And this ratio determines the type of void to which the cation enter, and the kind of coordination and the structure type is decided by this radius ratio. And it is that when radius ratio increases, that means when radius of cation increases or that of anion decreases, coordination number will increase. That is what is radius ratio rule. You can see the limiting radius ratio given here, the range. You can see the radius ratio is increasing down and the coordination number is increasing. The type of void occupancy changes from trigonal, that is the simplest void, the vacant space at the center of three touching spheres, which is relevant in the case of planar structures. And when it is tetrahedral void, it is 4, then octahedral void is 6, and cubic void it is 8. Say for example, let me show a cation, right? And I am keeping anions around it. Suppose this is the size of the anion, and let's say there are 4 anions around this cation. Now, what happens if we increase the size of the cation? That means R plus increases. I am drawing a bigger cation. And let me arrange anions the same size around it. Naturally, you can keep more anions around a bigger cation. That means coordination number increases. That is the point. When radius ratio increases, coordination number increases. That's what's happening here. Similar thing happens if you decrease the size of the anion. Let me take the same cation here, the same size, and I am reducing the size of the anion. Let me take smaller anions around it. Then also you can see coordination number is increasing. Okay. So that is what is radius ratio rule. Right. Now, when we consider the close packing of anions and cations in an ionic solid, ionic crystal, the point is that each anion will try to have maximum cations around it and vice versa. That is to have maximum attraction and maximum stability and lattice energy. But there is a limitation in the case of ionic solids. Unlike in the case of metallic crystal, the difference is that you need to maintain the electrical neutrality, right? So, the coordination in the case of ionic solid is found to be much less than that in the case of metallic crystal. You know, in metallic crystal, in HCP, CCP, close packing, the coordination number is 12, that is the maximum, most efficient packing, and because of that metallic crystals are having high density. But ionic crystals, the density is much is lower than that of metallic crystal, because here the coordination number is maximum possible is 8. This is because to maintain the electrical neutrality, you cannot have any number of ions around the opposite ions. Okay, now let's see the different types of coordination. See, when the radius ratio is within this range, that is below 0.225. What about this 0.225? That is the ideal radius ratio for a tetrahedral void. See, in the previous class we have seen this. This is a close packing of 4 spheres, which you can see in the CCP or FCC arrangement at many places. And the empty space inside this is tetrahedral void. If you keep a small bead inside this and take the ratio of this bead, that is the void, to that of the sphere, that is 0.225. Okay, so if the radius ratio is below this or coming in within this range, that will give a coordination number of 3, and the geometry, the structure type is trigonal planar, and that is the example is B2O3, which is having a layered structure. So 3 oxygen atoms make up the close packing, and boron will reside at the center of it. That's not very significant for us. The remaining 3 are important. When the radius ratio increases from 0.225 up to 0.414, what is 0.414? That's the radius ratio for octahedral void, which is bigger. So up to this, it will have tetrahedral arrangement. That means if it is 0.225, that means you have a cation which is exactly fitting this void, that is 0.225, correct? Suppose the cation is a little bigger in size, then what happens? Then these 4 anions, suppose, will slightly open up so that cations is accommodated. They may not be then touching each other. And that will continue until the radius ratio reaches 0.414. When it reaches 0.414, more stable coordination is, that is, more stable occupancy is entering into octahedral void, right? That means it changes into octahedral void. You know, octahedral void is the vacant space at the center of 6 stretching spheres. So coordination number will be 6. That means there will be 6 anions around this cation. So octahedral structure arrangement. An example is sodium chloride. For example, for this tetrahedral geometry is zinc sulfide. It's very clear, you know, zinc and sodium. Zinc is a D block metal having smaller size, and so Na plus is larger in size. So when R plus increases, coordination increases. Now when it exceeds 0.732, what is 0.732? That is the ideal radius ratio for cubic void. When it is within this range, then the coordination changes to, the occupancy changes to cubic void, and the coordination is 8. It's a cubic arrangement of ions. Example is cesium chloride. It's very clear. Na plus and Cs plus. These are alkali metals, and when you come down, size increases. Cesium is much bigger than sodium, so it requires a cubic type of void to enter. So it's very interesting to see how the geometry changes with the change in the size of the cations. Now we will consider mainly two types of structures. In the case of ionic compounds, that is, one is AB type. AB type means it's a 1-1 formula. Example NaCl and cesium chloride. And one example in AB2 type, that is 1:2 ratio, that is calcium fluoride. We start with sodium chloride. NaCl structure. NaCl structure, it is popularly called rock salt structure. Rock salt structure. This is a model structure. There are many other ionic compounds having the same structure, like sodium chloride, potassium chloride, magnesium oxide, etc. Silver chloride, etc. All are having the same structure. When we discuss the structure of one ionic compound, we have to emphasize on various points, like what is the radius ratio? That's the first thing. What is radius ratio? That means Rna plus by Rcl minus. The value is found to be 0.54. So based on the radius ratio rule, this comes in which range? 0.414 to 0.732. So it will be an octahedral occupancy. Then we have to explain the structure of the arrangement of each ions. We have to describe the arrangement. That means how Na plus is arranged, or let's say first of all the anions which make up the close packing, how Cl minus is arranged and how Na plus is arranged. Cl minus is arranged in FCC pattern or CCP. Okay, that is, the anions make up the close packing, and Na plus occupy all the octahedral voids. So that is a kind of arrangement. As I said, it is an octahedral occupancy. So Cl minus is arranged in it is arranged in FCC or CCP pattern. There is a close packing, and Na plus enter all the octahedral voids. We can look at this model. This is exactly the unit cell of sodium chloride. You can see that already we discussed this structure in XRD techniques. See, the green balls represent Cl minus. What is the arrangement? All the 8 corners, and also there is one at the and also all the face centers, you can see Cl minus, all the green balls. So this is FCC arrangement, right? So when it is FCC, what about the effective number of particles? It will be 4 Cl minus, right? Because in FCC, Z is equal to 4. Effectively, there will be 4 Cl minus in this unit cell. What about Na plus? In all the octahedral voids, see, we have learned that number of octahedral void is equal to the number of particles. So when there are 4 effective particles, there will be 4 Na plus also. Okay? That means, therefore, the number of NaCl units present in one NaCl unit cell will be 4 NaCl units, because there are 4 Na plus and 4 Cl minus in one unit cell. So the total number of NaCl units present in this unit cell is 4. Okay. Now the next point is, what about the coordination number? coordination number. It's very simple. Already we have learned that it is an octahedral occupancy. That means coordination is what? 6. That means around each Na plus there will be 6 Cl minus and vice versa. So we say in the case of ionic solids we should mention 2 numbers, that is the coordination number of cation as well as anion. In the case of AB type both the numbers will be same. So coordination number is 6:6. What does it mean? Around each Na plus there are 6 Cl minus and around each Cl minus there are 6 Na plus. You can understand it from this structure itself. If you look around this, okay, coming back to the arrangement, I told you Cl minus in FCC, Na plus in all octahedral voids, right? So where are the octahedral voids? In this cube you can see that we have already discussed this point earlier, that all the edge centers are part of the octahedral voids. How many edges? There are 12 edges. So all edge centers. So 12 edge centers and one at the body center. You can see this one is exactly an octahedral void. This is Na plus and it is an octahedral void, because if you look around the Cl minus and join them, see, let me connect this chloride into this one and into this one. So these 4 Cl minus make a square and there is one above and one below and join from to all these corners. It is an octahedron, right? So Na plus is at the center of this octahedron, so it's octahedral void. So edge center as well as this body center are octahedral voids. You know the contribution of an edge is how much? 1/4. So 1/4 into 12. See how you get this 4 Na plus. You can also say 1/4 into 12. That is the edge contribution, plus there is one octahedral void right in the body center that is completely belonging to this unit cell. So how much it comes? 3 plus 1, that is 4. You get the same number. So that is how. So that is the arrangement of NaCl, the structure of NaCl, rock salt structure. See, it is interesting to practice how to draw this structure. See, you can draw the structure of NaCl like this. Drawing a big cube, it's a simple practice only. First you will draw a big cube, and then what you do is you show the chloride ions in FCC arrangement or CCP arrangement, the chloride ions. So that means all at the 8 corners. And all the face centers. So you can show them at the face centers, all 6 face centers, right? One will be here and one will be here. And then what you do is you divide all the faces into 4 equal parts like this. Passing through this, you can draw them, you can divide them like this. All the faces are divided into equal 4 parts. And this is done to get the edge centers to show Na plus. That is the point. That is why we are doing this. Okay. This will come like this. And this is to be divided. Okay. Finally, we will join this. Opposite faces are also joined. All the opposite faces are also joined like this. So by doing this, we can now show Na plus, where in all octahedral voids, that is all the edge centers, 12 edge centers. You see, I am showing Na plus like this. Edge centers are shown. Na plus is shown at the 12 edge centers. You have to be very careful in locating these edge centers. Okay. All the edge centers we are showing Na plus. And finally, So you can see 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 1 Na plus is there at the body center. Okay, it's over. And this is the structure, sodium chloride structure. Okay, so that's interesting practice. Let us go to remaining two more structures. What's the next one? In AB type we have cesium chloride, right? Cesium chloride structure. The second one, cesium chloride structure, which is otherwise called pseudo BCC. I have told you about this in discussing powder diffraction pattern. BCC, so cesium chloride is actually having a primitive lattice or primitive cubic lattice or simple cubic lattice, but it appears to be BCC. Okay. Another point regarding sodium chloride structure is that this structure can also be explained in another way, like what we did in diffraction technique. Sodium chloride is consisting of two FCC lattices, one that of Na plus and the other that of Cl minus, which are halfway interpenetrated. That way also we can explain the structure of NaCl. Coming to cesium chloride, first thing is we note what is the radius ratio. RCS plus by RCl minus is found to be 0.943. So this range belongs to which kind of void occupancy? Cubic void, isn't it? So that means the arrangement will be like Cl minus is having a primitive cubic or simple cubic arrangement, and Cs plus enter all the cubic voids. So this is a kind of arrangement. How does it come? The structure of cesium chloride can be very simply shown, because the unit cell of cesium chloride need to be very small actually. Let me draw a very small cube, right? And I am showing here the chloride ions in simple cubic arrangement. Okay, that means only at the 8 corners we have chloride ions. So these are chloride ions. And what is cubic void? The empty space at the center of this cube, that is cubic void. So I am showing cesium ion here. This is cesium ion, Cs plus, and these are all Cl minus. So structure of cesium chloride is that Cl minus is arranged in primitive cubic array or primitive cubic lattice, and Cs plus enter the cubic void. So altogether this looks like what? A BCC. But it's not exactly BCC, because the particles are not the same. The particle at the body center is different from those at the corners. So it's not exactly BCC. That's why we call it pseudo BCC. Now what is the effective number of particles per unit cell? Cl minus being primitive cubic, it is 1 by 8 into 8, so Z is equal to 1. So 1 Cs plus, sorry, 1 Cl minus. Okay. Then what about Cs plus? Only 1, because that is at the body center. So Cs plus is also 1. That is 1 Cs plus is present. So Z is equal to 1 cesium chloride unit. So the point is the number of cesium chloride units present per unit cell is 1. Whereas in the case of sodium chloride it was 4. So here cesium chloride can be described by this small unit cell. Okay, let me consider this model, and I am explaining cesium chloride using this. Listen well. Suppose all the balls are green. Okay, that means this gray ball is also green. You suppose all these balls are green. So now you consider only this small cube, okay, which has 8 green balls at the 8 corners. Suppose it is Cl minus, like this. So Cl minus in primitive cubic arrangement. And then this will be, of course, you know, these are not so small, they are big enough to touch each other, right? And cesium ion is kept here at the center, that is the cubic void, okay? So this is one unit cell. And let's suppose there are more unit cell all around here. That means there are 8 such small cubes here. So there are 8 cesium chloride unit cells. There will be cesium ions at the center of each cube. You understand? There will be cesium ion at the center of each of these 8 cubes. Now, you see, let me join these 8 cesium ions. What you get? You get a cube. And at the center of that cube, what is there? This is not gray, this is green, right? This is chloride. That means it is now like chloride ion is at the center of the cube formed by 8 cesium ion. That means the coordination is reciprocal. If there are 8 Cl minus around Cs plus, there will be 8 Cs plus around Cl minus also. So the coordination number here, coordination number in the case of cesium chloride is 8:8. What does it mean? Around each Cs plus, there are 8 Cl minus and vice versa. Okay. Now finally we go to the structure of an Ab2 type, that is calcium fluoride. Okay. Ab2 type. In Ab2 type we have only one example, that is calcium fluoride structure. Structure of calcium fluoride. It is also known as fluoride structure because the name of this mineral fluoride. See, in the case of cesium chloride, there are more examples, you may note that, like cesium bromide, cesium iodide, thallium chloride, etc. They are also having the same structure like that of cesium chloride. Now, the structure of calcium fluoride or fluoride structure is also there for thorium oxide, is also having the same structure. Okay. Now, when we explain the structure of calcium fluoride, first thing is we look at the radius ratio. So, radius of calcium 2 plus by radius of F minus fluoride F minus is found to be 0.75. So this value suggests that the occupancy is to be again cubic void because it comes in that range above 0.732. So cubic void. That means F minus will be, so we will go to the arrangement. F minus, that is the anion, will have again a primitive cubic arrangement, so that there will be cubic void for Ca2 plus to occupy. But an interesting difference here is that this is a 1:2 type solid. So to maintain this stoichiometry and maintain electrical neutrality, we have to be careful here. When it is F minus is in simple cubic arrangement, here to explain this structure, let us consider the unit cell as this big cube, and as I said earlier, here F minus, that is the anion, right? F minus is arranged in primitive cubic. That means all these boards are same. Suppose all are green. So this is primitive cubic arrangement, right? Isn't it? If you take this cube, there are particles only at the 8 corners. All are green, that means F minus. So there are so many such unit cells here. So primitive cubic arrangement of F minus. Okay. And so what about the effective number of particles in this? You know, if one cube will have, since only 8 corners, particles are there on 8 corners, what is that? 1. So there are 8 such cubes. So effectively there are, in this big crystal, there are 8 F minus. You understand? I am taking the whole crystal for explain the structure. I will tell you the reason. So there are effectively 8 F minus, and there are 8 cubic void also, because at the center of each cube it's a cubic void. How many calcium ions are required to maintain the charge? For 8 F minus you need only 4 calcium, right? Because Ca is 2 plus. So 8 minus will be balanced by 4 Ca2 plus, because it will be 8 plus. That means only 4 calcium ions are to be entered into the cubic void. So how you arrange? Ca2 plus ions are occupied in half of the cubic void, not all the cubic voids. That means if there is calcium ion here, it will not be here. It will be here, not here. So it comes like this. That means we can say calcium ions enter alternate cubic voids or half of the cubic void. So it will be here in these two, and below it will be in these two, isn't it? It comes like this. Okay, so you will have calcium ions here and at the center of these two cubes. So with respect to calcium ion, there are 8 F minus around because it is in cubic void. So coordination number for calcium is 8. But what about the coordination number of F minus? It will not be same. The number will be same for AB type. In AB2 it will be just opposite. Like if this is 8, then the other will be half of it, that is 4. You can understand. That means in the case of calcium fluoride, coordination is 8:4. That means around each calcium there will be 8 F minus, and around each F minus there will be only 4 calcium. You can see it here. As I said, calcium is there at the center of this cube and this cube. Similarly below in these two cubes. Okay. Now you look at the body center. What is there? This is which one? Green ball, that is F minus. So around this F minus, how many calcium? There are 4, which are arranged in a tetrahedral manner, isn't it? Okay, so the coordination number of F minus is only 4. So coordination number is 8:4. Arrangement is F minus in primitive cubic, Z is equal to 8 F minus, calcium in half of cubic voids, only half of cubic voids. That means it will be 4 Ca2 plus. So altogether the number of formula units present in the unit cell is 4 CaF2. And finally the coordination number of this crystal is 8:4. It means around each calcium there are 8 F minus because calcium is in cubic void, and around each F minus there are only 4 Ca2 plus. This is the arrangement. So these are all about structure of ionic solids. With this we come to end of this module. Thank you.